don't know if I was supposed to take the box, but I took the box.
I think you can do whatever.
Thanks.
Feel
All right.
desires.
Cool. I'll fall back on that if anyone questions me. Alrighty. Let me get the next homework assignment up on the board here first. I imagine Kyle will show. It's not like Kyle to not show and not tell me. So, I got, what chapter are we on?
5, I think?
Is that right? Yeah, that sounds.
5 or 6, I'm not really sure.
Yeah, that's what I'm thinking too. Let's read it.
Just to wrap up
Okay. So 6. Awesome. Perfect. This is chapter 6. And let's shoot for next Wednesday. I think this is doable. This isn't a big assignment. So back, like the last one was a little bigger just because of the break. Cool. One note that I forgot to make while we were going through the permutations. What's up? You okay?
just forgot to do my own example. Oh, so it's right. You're still.
Oh. Oh.
That's on me.
Okay, okay.
Sorry.
That's okay. It's not for this class, is that what you're saying?
No, it is for this.
It is for
But
this.
it's not.
Okay, okay, cool. You mean like on the new material?
On going back through how to go through the cyclic groups and like I was gonna do examples just to make sure that
Should we just start off with a problem just to warm up?
I wouldn't be mad at that.
Let's do that. Let's just do that. Is that okay? Yeah.
This is chapter 6 is on isomorphism. That is the correct chapter, right?
That is correct, ma'am. Yes, that is the isomorphism chapter. First, so what kind of example were you going to do? Like a cycle problem of some kind?
it's any time that like you're multiplying the two groups
Yeah.
together and with the disjoint cycles and making sure you do it right.
Okay, awesome. Let's multiply a couple together that aren't disjoint. Does that sound good, or would you?
Or yeah, to get them into disjoint or
Oh, okay. I think I know what you mean. Okay, so how about this? What is the order of good morning? And I don't know what S yet. I gotta start writing stuff out. Probably 6. Sigma if sigma equals 2, 3, 5, 1, 3, 2. No, wait, that one. Yeah, whatever. And then, yeah, that could be good. And 6. No, make that a 6. Yeah, that'll be better. 3, 4, 5, 6. Okay, that's. Do I have every number in there? 1, 2, 3, 4, 5, 6. Okay, cool. What is the order of that permutation? So first is put it into disjoint cycle form. That'll be a step 1. And Diane, I did get the thing you put in my basket, so good to go. And if it's not obvious, I have no idea what the answer is. It's kind of interesting.
balance transposition?
That's if it's even or odd.
Okay.
So to do the order, we want to break it into disjoint cycles and then find the least common multiple of those cycle lengths. Does that sound, yeah? Yeah, and let's actually add I like your problem. Let's determine if this is even or odd as well. All our answers are probably going to look different. Yours is probably going to look way different than mine, unless you started with 1. I usually would have started with 6, but you can start with anything you want. So we'll make sure that we reconcile any apparent differences.
Personally, that's the step I'm most confused about.
Yeah, I might, hold on, I'm worried, I'm a little worried I did something. Which step did this?
It's the writing them as disjoint cycles.
Okay, do you want me to talk it through?
Yes, please.
Okay. Well, we can check it. If you've got it done, we can check it out right now. So pick any of the elements you want, and imagine feeding it into this thing. So I'm feeding a 1 in. So I chose that 1 to begin. I could choose any number I want. So I look to see if I encounter a 1, and the first time I encounter a 1 is right here, and that changes the 1 to a 4. And then a 4 passes out of this thing. You can think of each of these things as doing something to each number that it gets. This takes 1 and moves it to 4. This doesn't touch 4, so when we come out this way, the 1 has become a 4 and that's it. Does that make sense? So then I look at what I just got out of there and I feed that back through Sydney. So I'm gonna go to a 4. 4 goes to 5. This doesn't touch 5. This touches 5 and sends it to a 2. So I actually totally screwed up. And that was right, because I was I was worried there because I was starting to have a non-disjoint cycle. So I'm not sure that that's the end of it. I gotta keep going. Yeah.
So then you feed the.
Yeah, so you'd help me work this one through. What happens to 2 now?
We have to feed 2 back in.
Yep. What happens here?
Nothing.
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 And then 2 goes to 3.
And that's it then, right?
3 doesn't get touched again.
3 doesn't get touched again. Now what happens to 3?
Feed it in. So 3 goes to 4. 4 goes to 3. 3 goes to 5. And then I feed 5 in.
Mm-hmm.
5 goes to 6. 6 goes to 1. That one's done.
So
it wraps around.
It wraps around. Perfect. Is this agreeing with what? So it looks like the 6 is probably fixed. But let's verify. Right? So 6 goes.
6 goes to 3. 3 goes to 6. And it's done.
So I could write that. I don't need to.
Okay.
So that actually took. So the LCM here is pretty cake, right? What is our order? 5. Yeah, and it's just the number of things in the cycle, right? So right here it's just 5. cool. Trinity, is that like sating your need to have an example? Awesome, awesome. So this one, we don't really need to go into a cycle of transpositions to answer this, but let's do one anyway. So sigma, this is sigma. Sigma could be, and there's a couple of schemes, and I'm gonna go with the one that just is easiest for me to remember, the pairings. So 1 goes to 4, 4 goes to 2. I think this works, we're gonna check it out. 2 goes to 3, 3 goes to 5.
You don't need 6.
And we don't need 6, that's right. So I think that's right, but I wanna verify this myself because it does worry me a little bit. So let's see, I wonder if there's a better way to do that. Let's just do this. So this first one changes 3 and 5. So the next position after this one, this is what I've got, and then this changes 2 and 3. And then this changes the 4 and the 2. And then lastly, we change the 1 and the 4. And we have to put this into cycle form. So like a lot of, when I was first like getting ready to talk about all this stuff, I would get confused and I would look at this and go, oh shit, it's not right. But this isn't the cycle representation. So what we actually need to do is look at the net effect of this whole thing. From here, what is happening? And so that means in cycle form, so let me show you how to do this. 1 goes to 4 inevitably. Yeah, and then I go to 4. 4 goes to 2, 2, 3, 3 to 5, 5 back to 1. Now I know I'm okay. And just keep in mind that, you know, if I'd had this, that's also cool, right? Any rotation of these things through there, the wraparound covers you. Sound good? So we are even. But I could have answered that question back here. Once I'm in a disjoint cycle form, a cycle, notice there's 5 things here, which requires 4 transpositions, so it's even. It's just 1 less than the number of, so if the cycle length is even, the cycle is odd, the cycle vice versa. Only in disjoint form. Anything else we want to talk about with permutations? Like feeling like on top of it, awesome. Diana, you feeling good about this stuff? Yeah. Nice. Beautiful. All right. Good thinking. So there is one last thing I wanted to say about these permutations. When we talked about the group S of M, what is this? Without looking, what is this? Because I can look it up.
It's the symmetric something set.
Symmetric group.
Group.
Yeah.
Okay.
What does it represent?
It's like the set of all permutations
On.
1 through N.
Yeah, oh, look at you with now notes. And you've just become like 10 times more powerful because you know you can do it, right? So beautiful, Sydney, thank you. Awesome. So the order of that group, we never did talk about the order of that group, but let's do so. Everything in this group is a list of 6, we have 1 through 6 to put in 6 different slots. How many ways can I do that? Like how many different strings of 6 digits from 1 to 6 can I make? It's a counting problem. And I know some of you had, you've had combinatorics, no?
Mm-mm.
No, none of you have, okay.
Is it like a factorial thing?
It is. It is a factorial thing. So how many things can go in the first slot?
6.
6. And then how many things can go in the next slot? because I've used one of
Oh,
them,
okay,
right?
5.
So 5 and then times 4. And you multiply these all together, 3, 2, 1. So 6 factorial would be the number of ways to do that. So this is n factorial.
Okay.
What is the order of the alternating group? And first off, what is the alternating group?
Does that have to do with the even,
Yeah, it does. It's just the even permutations. So it's all the permutations out of here that are even, and it's literally half of them. What is the order of that? Did you say 3? It's always 3. No,
Yes.
no. I mean,
Um,
it's half of these.
n factorial over 2.
There, look at you. Very beautiful. Thank you, ma'am. Might come in handy at some point in the future here. Possibly today, possibly next month or something. Okie doke. Good review. And it didn't take too long either. So, without looking at your notes again,
Alright.
what is an isomorphism? We've got two groups. We've got group G, we've got group G prime. What is an isomorphism between those groups? Did anyone read the chapter yet? I guess that's what I'm asking.
No.
Okay, then, yeah. No, but, yeah. But,
When you, because you talked about isomorphisms a little bit earlier, and
Mhm.
it's not an equal sign, it's an equal sign with a little thingy on top.
yeah, and in fact, our book actually does that.
Okay.
Yeah, means.
Yeah.
Yeah. Like in just plain language, can you maybe, without like a fancy?
Like they're kind of the same, or they are the same?
They are kind of the same. I think I like your first one, and I think the combo of them is a nice thing. They're kind of the same, they're the same. But not really the same. But pretty much the same. So what do we mean by that? So what do we mean by this? We mean that there exists some mapping from G to G prime that is 1-to-1 and onto. So in other words, a bijection. And this syncs up the elements, right? This is just saying for each thing here, I've got a companion over here, and no two things here go to the same companion. There's literally, you can line them up and perfectly match them up. But we're in algebra class, so it's not just that. There's some algebraic stuff that also goes on. So we have this bijection between G and G prime that preserves the group action. And that's it. Such that such that for A and B in the domain G, if I take phi of A times B, and this is let's be really careful with this. This is the product in G. So we don't know what, and that could be addition, that could be composition, that could be multiplication, it could be something weird ass that we've never encountered yet. But if I take two things and I multiply them together in G, I'm gonna try to do a picture. No, I'm not. Drawing pictures for this stuff is always a bad idea, I think. Is equal to the image of A times the image of B. So yeah, I'm trying to think, can I draw a picture of that? I don't think I can. But I think it's best understood by example. We've been actually kind of doing it already. So examples. Let me make sure I got the entire definition actually correct. Yeah, I didn't even write it down. I thought I knew it so damn well. So let me just double check myself. Make sure I'm not lying to you. Yep, that's it. Yep, cool. Wow, damn, I did it. Nice. Look at me. Yeah, nice, indeed. So let's do some examples so we can get a sense of this. Let's start with an example we've already been using as a tool for thinking. So I've got an element of a group G, and the order of that element is 5. So I know that a to the 5th gets me back to the identity. So this is a cyclic group of order 5. Right? Once I've got a group element of finite order, I can think of it as I can think of it as generating a cyclic group. So we've got this A that consists of a to the 0. I'm going to write it out like that. We know that's E. Whoop. E squared, E cubed, a to the 4th, and then a to the 5th gets me back to the identity. So let's just make a little note here above it. I want to put that above because underneath I'm going to draw something. What is that the same as? What have we been saying that's the same as?
Z.
Yeah, which Z?
Z5.
Z5, beautiful. So this, let's call this G. I wish I wouldn't use G already. Let's call it H. Equals that in the subgroup. H is isomorphic to Z5. So when I claim this, if I want to claim this, I need to demonstrate the existence of the mapping. So let me write that all up. To show this, we need to produce a phi from H to Z5 that is 1 to 1 and onto. That preserves the group action. That also preserves group action. Alrighty, so just like really quick, what is the operation in H? I didn't really make it clear, but how do these elements interact? So like for example, if I took a to the I times a to the j, what is that equal to? How do I figure out what that's equal to here? Well, how about this? So we get a little sooner. What's a squared times a squared? And this times is the group operation.
Isn't that a to the 4th?
Yeah. So it kind of acts like multiplication. So you want to say multiplication, but you got to keep in mind, this could be something weird. It could be an operation that we don't understand. It's not multiplication in the classic sense, but we can call it multiplication here. So it's just a matter of adding exponents, right? To multiply any two of these things, we have to add exponents. Oh my God, sorry. I'm starting to get a hunger attack. It's like, it's bad, because I've been drinking a bunch of tea and it gets the tannins. Ugh, like, I don't want to vomit in front of you, and you don't want that either.
Probably not.
Yeah. Glad that's on tape. Tape.
You just aged yourself a few
I
years.
know, I know, I know. Play it on the Victrola. Sorry, let me just finish this bite. It's better me to finish this bite than to lose all bites. Okay, so, let's see, what do we got here? Where was it? Okay, so we need to produce a mapping to Z5. Let's write out what Z5 is. And I want you to maybe help me figure out what to do here. There's Z5, and what is the operation here? What's the operation in Z5?
Is it multiplication mod n?
It is not, it is something mod 5, but it's not multiplication.
Addition?
It is addition, mod 5. So the Z groups are all addition. And up here, it's just multiplication But we have to be careful because, like, what if I took up here a cubed times a to the fourth? What would that be in this group up here?
Interesting.
Good.
So it's a to the seventh, but a to the seventh is not in the group.
I like that. So yeah, a to the seventh makes sense. Yeah, I got 7 a's multiplied together.
But it's a to the fifth times a squared because, and then a to the fifth is just e.
Oh, look at that. That is so
It's a
beautiful.
squared.
You were on fire. Literally on fire today. So that's a squared. So that's just a squared. Notice that it's actually just the exponent mod 5.
Okay.
So like if I took a to the fourth times a to the fourth, that would give me a to the eighth. 8 mod 5 is 3, and I can just do that kind of quickly like that. So you're starting to see, can you see how it might be a close relationship here going on? Awesome, so it's multiplication, and we mod 5 the exponents. All right, so let's start building our phi. Phi of a sub I, where do you think I should send that? A to the I. Where should I send that in Z5? So here's an L, this is in H. I want something in Z5, so it's gotta be a number 0 through 4. Sounds like a pretty reasonable thing, right? And when you look at the matchup here, that's gonna do it for us. So this is our claimed map. And this one is so finite. It's just got 5 things in it. We can just write it out and verify 1-to-1 and onto easily. When things get infinite, things get a little weirder. But here, life is good. So, so let's let that for I equals 0, 1, 2, 3, 4. And so phi of E in the original group, where does that map? And that's a to the 0. So that's gonna go to 0. Yeah. Which is the identity in Z5. So notice that, let's just make little notes here. Identity gets mapped to identity. This is a characteristic of all isomorphisms. They carry the identity of the one group into the identity of the other group. Phi of A, what's phi of A?
1.
1, beautiful. I think we see how this is gonna work. I know you can read exponents and copy them over. So when we look at this, you can see just clearly that that is 1-to-1 and onto, I think, and I hate using that word clearly, like the little mathematician inside me slaps me. The little good mathematician on my shoulder slaps me. The evil one makes me say it. So this is 1-to-1 and onto just by inspection. I don't think I've ever used that phrase, or I haven't used it in a while, so that's a great phrase. It's just mean, look at it, dude. There it is. So, we got that. We have to make sure it preserves the group action, and then we're done. So, check that phi preserves the group action. So that means I'm going to take an element from my cyclic group times an element from the cyclic group as well. So I've got I and J. I and J run from 0 to 4. This is equal to, so let's work this through. This would actually be phi of A of I plus J. just using the group action inside the group action in a cyclic group, you just add the exponents, that's all I'm saying there. What is that supposed to be according to our definition? What does this have to spit out as we defined it?
Wait, you modify the exponents.
A little more, yes. Let's actually, yeah, let's be clear, you're right, Sydney, let's put a mod 5 there, just to be safe. I think we really need to do that, because if these two add up to something more than 4, we're not doing good. Things aren't gonna go well. So, yeah, it's just the exponent mod 5. So it's I plus j mod 5. Now, let's think about where we need to go. So I need to get that this is phi of a times phi of a to the j I times phi of a to the j. What would this look like? Oh, wait. Whoa. Yeah, actually, what is the operation here? So I'm writing multiply, but I gotta be more careful because it's not really multiply for us. Remember that the output of phi, this is in Z5, and this is in Z5. What do we do in Z5? Addition. So when you're doing these isomorphisms, you have to really be mindful of the operation in the group. Now, I could write this and just assume that you understand, or the reader understands that it's plus, but let's be really explicit, because this is the op in Z5. And so this would just be I mod 5, this would be J mod 5. Do we have that now? So in other words, what's the next step in getting this to here? And we're gonna proceed slowly. What do I wanna write next so that it's really evident I understand what's happening? Look at this flow. Here's what we need to get. We need to basically come up this direction to get back to here. What's the next slow step here? I have 2 things added mod 5. What can I do with those?
Just split them up.
Split them up. Yeah, right. And that's great, because that's the next step here. And once I've got that, I just write this chain up. So this is I mod 5 plus J mod 5. And then that is, this is the definition. This is literally the definition of phi of a to the I. And this is the definition of phi of a to the j. And I'm done, because I've shown that it preserves the group action, that doing this stuff here before taking phi is the same thing as doing phi, then doing the group action in the other side. So check, it preserves group action. And then here I would say thus, phi is an isomorphism. And H is isomorphic to Z5. So this is kind of how every proof will go when you're asked to show these 2 things are isomorphic. When we want to show 2 things aren't isomorphic, we're going to need a few properties of isomorphisms first and show that those get busted somehow. Let me let you get caught up writing. It's a good time for me to avoid throwing up. And neutrify at the same time. Wow.
Nutrify?
Neutrify.
Absolutely. Okay.
Okay, so let's see. Let's do some more examples. Today's a very example-y day. Is it okay if I start erasing here? Anna, you cool with that?
Don't have too much fun without me in the next 5 seconds.
Okay, okay. next? Oh, here we go. Oh, actually, I have a little note to myself. Look at, let's see here. Hold on, let me look here. It says, see page 128. I wonder what I was, nah, fuck that. We don't want to look at that. That'll be fine. We'll be okay. When you read the chapter, you'll see the table on page 128. It'll all be great. Let's just do another example. So let's let G be the reals under addition. And let's let G, the book uses this G bar, so I'll go with that notation. As long as it's just a different letter or symbol, you're good to go. So this is going to be the positive reals under standard multiplication. Okay. Wow. We should have like little chamber pots under the table.
No.
No? Okay, all right.
Wrong.
We won't, I'm sorry. I'll take that back. And noise canceling headphones or something like that. Okay, so convince yourself for a second that this is a group. What is the identity in this group? 0. Beautiful. How do you do inverses? If I have an element A in this group, what's its inverse? Beautiful, yeah. So A inverse is just negative A, nice. And then you add two real numbers together, you get a real number. There's nothing intense going on here. What about in this one? What's my identity?
1.
So yeah, so here, 6 equals 0 there. Down here, E equals 1. And what does inverse look like in this? So if A is in G here, what's its inverse? 1 over A. And let's do that instead of the A inverse, because that's not helpful to us anymore. That just means, inverse to us, so it's literally just 1 over A. Yeah, beautiful. And we avoid 0, so there's no problems. Cool. So we need to come up with a map that turns addition of all the reals into multiplication of the positive reals. Now I'm not going to ask you to come up with one because we could probably spend a long time here trying to rack our brains. But I'm going to give you one. Let's let phi of A, or how about phi of X, let's put an X in there, equals e to the X. Let's actually just draw that graph really quick. Because we do have reals, we can actually sketch a little graph. And we don't need this negative part here. So here's R plus, here's R, and here's the graph of E. Yeah. And you can kind of see that it takes the identity from 0, or from the first group. This is my G down here. This is my G bar up here. It takes the identity from down here and maps it to the identity in the other one. So you can kind of see that from the graph. So that's very nice. So it'll make it easy to verify a bunch of things. How do I show something's 1-to-1? So need to show, let's just say step 1. Phi is 1-to-1. How do you show something's 1-to-1, dear graduates of MT423? While I further neutrify.
Quick question, is
Mhm.
the e to the x, is that's your G bar, right? Or is that?
That is the function. G bar is this group.
Uh-huh.
So G bar is this axis with multiplication. G is this axis with addition.
Okay, so you're putting something from G into your phi function to, okay.
Yep. And I could actually use any positive number here. I think like when the book does this example, they use 2. You could use anything you want. You could put pi here because the graph looks essentially the same.
Mm-hmm.
So like any a to the x where a is positive looks like that.
Yeah.
They all look the same, but I like E. I'm a big fan of E. I'm kind of an old crank about Pi Day. I get really cranky on Pi Day. Everybody's so excited about Pi, and I'm always just like, fuck Pi.
I was excited about Pi Day in middle school when we had a pie party.
Yeah. I mean, you get pie, you know.
Yeah.
I love pie. No, you don't like pie?
I don't like pie.
Well, you can,
What?
like the food as a whole.
Yeah.
I know, I'm starting to like get
Oh,
scared.
Only
I'm
pumpkin
gonna come
pie.
over here with Sydney,
Okay, but pumpkin
recoiling in
pie-
horror.
It's the best pie,
Yeah.
and you can't change my
What?
mind about
Oh,
that.
now I'm recoiling from you.
What do you mean?
As you say this
What?
god awful
What?
thing, this
Diana?
pudding pie is the best pie.
Listen. Actually, I don't have an argument. I just don't like pie.
You don't like any pies.
I just like pumpkin pie.
Diana, step
and
in
that
here.
is-
Please, thank you. What's your opinion on pumpkin pie?
It's good.
Do you like, but you like all other pie, right?
What's your
What's your
favorite
favorite pie?
Cherry.
Oh.
Yes, now there. I'm
No,
coming over here.
I just don't like warmed fruits. Something about it is just like,
You can eat cold pie.
That's fair.
I know, but it's not this. Like.
Is it a
cooked
texture
fruits?
thing or
Yeah.
a taste thing?
Oh,
It's a texture.
Oh,
Cooked
you're-
fruits are the
okay.
I can't do like jam and jelly for that reason,
Mhm.
but like I'll do apple pie.
Where am I at? What is happening? I gotta wake up.
We just disappointed him.
I'm just broken. No, so I a cherry pie, a blueberry pie. Ooh. I will eat a pumpkin pie if pressed. I won't turn it away.
If someone insists.
If
that
someone
you must
insists
take a
I eat
bite.
that damn pie, like my mom loves pumpkin pie. It's so gross.
Meat pie is disgusting.
What?
Meat pie? Yeah, no, that just, even the
That's
phrase is just horrible.
That's wrong.
That's like an insult to call someone that.
That's British pie.
Yeah, the British pie, like kidney pie or something. Like, what's the
Ew.
deal?
Ew.
Yeah.
British pie or something.
Yeah, the Brits are weird. They really are. Yeah, that's just god awful.
Saw a TikTok the other
Key
day.
lime.
Hey, not bad.
Okay, all right.
Not bad.
All right, we're coming back together. We're finding some common ground here.
No, our common ground, our only common ground is pumpkin because that's the only thing Trinity likes.
Wait, you said you do like pumpkin pie?
Mm-hmm.
Oh my god, I missed that.
But only like I can only take it in small amounts. I can't.
Could you? So you could do a sweet potato pie.
How about the whipped cream on top?
It has to be there.
Okay, I agree with that.
Can't eat
Yeah,
it. Otherwise,
yeah,
I can't eat
We
it.
have found our
We gotta quit while we're ahead
joining.
here.
Yes, we're all together now. Finally.
Sorry about that.
No, that was great. That's good. Oh, yay.
How do
All
you
right.
show a function as 1-to-1?
We cannot avoid the discussion of this by distracting me with pie. If we had a real pie, possibly.
So 1-to-1 is where every element of like your first function maps to a single element of your other one.
Well, that's always the case. Because every function can only have one output. So the way you got the right idea, just your language
Or
is
like
a little
no
more precise.
output gets output twice.
Yeah, yes. That's a better, I like that, right? No two different inputs produce the same output.
Or okay, yes.
So let's write the definition up here. So we would say that a phi is 1-to-1 if I have two different outputs, implies that the outputs have to be different as well. So that's one characterization. But that's not a great one to work with. It kind of sucks because you're like, it's always a terrible way to start a proof where you go, assume x is not equal to y. Then gee, there's only about 1 billion ways that could happen. So what's the contrapositive of this statement?
Ooh. Okay.
Graduates of MT401.
This is like one of the first things we did.
Uh-huh.
If phi of x is equal to phi of y, then x equals y.
Yes.
God, you're good.
That is good. Yes. Yes. No cherry pie for you.
Proud of you.
Yeah.
Equal.
So proud of you, but we won't make you eat warmed fruit pie. So this is the way to go. When you want to actually demonstrate a function is 1-to-1, this is the way to roll because you've got the definition of the function and you can write that out. So here we're going to show phi is 1-to-1. So we assume phi of x equals phi of y. that means, go to the definition, e to the x equals e to the y. How do I undo e?
Unnatural log.
Oh, beautiful, natural log. So take ln of each side, and we get x equals y. It's simple, right? It's lovely. You could look at the graph and use the horizontal line test also, but that's not like a proof. We know that doesn't count, but you can intuit that it's one-to-one because no horizontal line hits it in two places or more. All right, great. How do I show something's onto? It never ends with me. It's just one thing after another, never satisfied. What does it mean to be on?
So that's where I'm stuck.
Every element of, like, say, G has to map onto every element.
Yeah, I think you got the right idea. Yeah, every element of the output. Yeah, right?
To hit every element.
So let's just do a little recall. A function f from A to B. So remember, this is the domain, and this is, what is this called?
Is it not called the range?
It's not.
Bummer.
Yeah, what the hell is it?
That's what I make it on.
It could be the range if we were on to.
Have to be.
But it doesn't have to be, right? You might not hit all of this. Sometimes this is just telling us, like, where is the output in general, codomain.
Oh.
Okay.
Yeah. And we may or may not attain all of f. So like for this function here, e of f, I could say this phi is a map from the reals into the reals. That's a reasonable domain, but it's not the range. Yeah. So is onto if, or surjective, right? Surjective, that's a lovely word. If for all b in the codomain, there exists an a in the domain such that f of a equals b, i.e. the range of f is equal to b. Yeah.
Such that.
Yeah, that'll sound like something you heard. Cool. So this is the way we show onto. This is the trick right here. So to show phi is onto G onto R plus. Take an element from the codomain and show there exists. You have to produce this x. Show there exists an x in the domain such that phi of x is equal to y. So let's just look at this equation. What would this mean? This would mean that e to the x is equal to y. What is x? And I'm asking you all to understand a function that it feels like very few people understand anymore. Fewer and fewer every day. I've already mentioned it, maybe not. Maybe we haven't, I don't see it on the board. How do I solve that equation for x?
Take the natural log of b.
Oh my God, yes! Pumpkin pie for all!
Yes.
Oh my God! Yes! So, take the natural log of each side. Beauty! So, we get x is equal to the natural log of y. And that is the element that hits y. So So the natural log of y is the thing I need to input to hit any particular y. Let's actually, let's see here. Wait, whoa, hold on a second. Oh yeah, we're okay. Why is this, so why is natural log of y defined? What is the requirement of natural log? So note that ln of y exists because what is the domain of natural log? Positive reals, yeah, because y is greater than 0. It's assumed to be because y is in the output group, which is the positive reals. Y is an element of the positive reals. Okay, awesome. So when you want to show something's onto, you literally need to solve this equation. Solve for x in terms of y every time. And sometimes it'll be like obvious. You'll be like, well, it has to be this. It may not actually involve solving anything. Like this doesn't feel like we're solving. These two relationships like are equivalent. That's another way to say it. In fact, to understand this, I usually tell most people, you know this, that's how you understand this statement. Logs are weird. Okay, so cool. So, okay, awesome. Thus, phi is a bijection from R onto R plus. Use that word onto there just to, because it's kind of, I don't know, you've already said it when you say bijection. You could say two, I guess that's also fine. All right, what's the last thing I have to show?
Oh, it preserves the group action.
Yep. Finally, we show phi preserves the group action. Outstanding. So, let's take x and y in our domain, and our domain is R. I'm going to write here, I always like to write what I need to show, so you know my guiding star is right there. I need to show that phi of xy is equal to phi of x, phi of y. What are my operations in the various spaces? So I wrote it kind of in that generic way. But what goes here? That's addition, yep. That's the, does that make sense to everybody? Because we're adding in R. Because look at G, right? Because phi moves from G to G bar, and here the operation is addition, here the operation is multiplication. Okay. So the inputs to phi are going to be added, the output of phi is multiplied.
Okay. So that's a multiply between those two?
Yep, exactly. Okay. Cool, so we need to show that. Can you just take that on for a second? And see what you can get. See if you believe that. Is this looking reasonable? Not sure yet, Sydney. Let's just start writing it out. So you start with this, right? Sometimes writing and letting the math guide you is the way to go. So I write out this left-hand side. What does that mean? What does this literally define to be? Yeah, e to the x plus.
Yeah.
And then you see it, right? Do you see it? Sydney, what's next?
Oh, I wasn't there yet.
Okay, sorry. I misread your excitement, sorry. What can I do with exponents that are added? Or what could I do?
Can you split them up into e to the x plus 4 times e to the y?
There you go. Yeah, is this what you were doing? Yeah. And now Miss Sydney, how can I rewrite this? What's e to the x in terms of phi? Yep. And you see now? Now you see. And that's d of y. And that's times. We got it. Done. So then we can just finally write here g is isomorphic to g bar. We've shown it all.
Nice.
Yeah, not bad, right? Like, there's nothing, like it's super deep, but like the computations, there's nothing heavy duty going on here, right? It's kind of like basic math. It's like pre-calc almost that we're doing at like this incredibly high view of all of it. Let's take a look at something in the book together. Oh no, actually, let's do one last, no, sorry. Let's do one last thing. And I think we might even get out a little early today, if that's okay.
Yes.
Is that okay? I feel like I need to make pie for everybody here. I need to bring a pie in one day.
Only pumpkin.
Only, oh yeah, I'm done.
Only pumpkin. And with the whipped cream.
Yes, it'll be vegan. It'll all be vegan.
Oh, that's fine.
Is anybody gluten-free in here?
No.
Yay. There's no way Kyle's gluten-free.
Oh God, no. No, absolutely
No.
not.
There's no way. Kyle, there's no way you're gluten-free, man. We've decided. All right, so here, I'm gonna ask you this last problem. And this, I'm gonna ask you to construct an isomorphism.
Construct an isomorphism.
Mm-hmm.
Okay.
Yeah, so what I want you to do, just take the last of it here, is show that Z under addition is isomorphic to, wow, isomorphic, missing some letters, isomorphic to Z, the even integers under addition. So it's a small step, but please construct your first isomorphism ever. And then just verify, do the verification. So build it, make a proper proposal for what you think. And it doesn't have to be phi. If you like another letter, your function can be that. It's phi. There's nothing special about calling it phi. It's fun to write phi. It's a pretty letter. Maybe we could call this group, we could call this one like 2Z plus, and that's also kind of a hint. Yeah.
Wait, so am I doing exactly like what we just did?
Yes.
Okay.
Yes, ma'am. So your step one is to come up with a phi. We'll call this G, we'll call this G bar. So your first step is to give me a formula here for a function that is one-to-one and onto between G and G bar. So we're on the same page. What do we think a good candidate for phi would be? Phi of x is what? Nice. Lovely and simple, eh? Good stuff. I'm starting to get a little, no, it's okay. I got scared. I got scared for a minute. I got scared about that preserving the group out. I didn't think there was enough twos, but everything's cool. Any particular points of struggle here at all, or just kind of like making sure you got the rhythm down right?
I think I got the onto part because you would solve, because it would be phi of x equals y, right?
Yeah, so let's take a y in the 2z, yeah.
So then,
So how did you go with
I
that?
did, so it'd be 2x equals y.
Yeah,
Okay.
yeah, it would. I think there's an easy, something, and I can see why there might be a little bit of like, how do I exactly get that? Since everything in 2z is of the form 2 times something else, that's what I would probably say first, just like go. So y is equal to 2k for some k in z, and then that makes it all like really clean. Is that where you were having some trouble, Sydney, maybe?
Well, yeah, cause then if you solve for x, if you do 2x equals y, then you get, x equals y over 2.
Yeah,
And it just didn't look,
it doesn't
Like I
look as
wanted.
nice. Yeah, I agree. I 100% agree. So this will get rid of that having thing. Then x would just be k here.
good.
Yeah. So let's see. Something like that. You might not have the exact flow. That's totally cool as long as we have the essence. And the 1-to-1, that's like cancel the 2 out, right? No big deal. All good. What about, so let's do group action together. So action, and it's addition in both realms. So that makes life simple. There's no chance of getting confused. So let's take x and y in G. Be really clear about that. Phi of x plus y is equal to phi, 2 times x plus y. Okay, and then now it's just algebra at this point, right? Like really, really lovely, old school algebra. Just be really explicit, and it's very simple, but that's it. That's all we need to do. And now we've demonstrated. And then you always just, add your thus or your hence or heretofore. No, I don't even know if that works there. Trinity could probably tell us if heretofore would work. Now that's like a weird, where do you use heretofore? Well, like you don't, you shouldn't.
Never heard it in my life.
Let's not.
Nice.
Yeah, cool. So I'm gonna ask you to just do me a favor, do me a solid, and start on the homework, please, because it's gonna be due on Wednesday.
Talk about it on Monday.
Yeah, I would love to talk about it on Monday. You might need to do a little reading, and hopefully that assignment will encourage you to, but if not, I would recommend just reading that Theorem 6.2 and checking out examples 7 and 8. Examples 7 and 8 are going to be super helpful. So Theorem 6.2 and example 7 and 8, and you don't have to worry about anything else unless you need to know what the definition of an automorphism is, and that's on the next page.
Bless you.
you. So there's like about 4 pages you could read and be happy with.
Cool.
Tops, 3 maybe. Thanks everybody.
The usage of that word peaked in 1912.
Heretofore. Yeah, it does.